Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 4. It's on Coulomb's law, which is a physics law, but also has huge ramifications when it comes to chemistry. And so if we look at a simple atom, this right here is helium. It's going to have 2 protons, 2 neutrons, and 2 electrons. What's holding those electrons around that nucleus is going to be Coulomb's law. And so if we were to look at the charges, the positive protons are going to have a positive charge, and the negative electrons are going to have a negative charge, and those opposites attract. That's Coulomb's law. And so that's the first thing that he discovered. If we have opposite charges, there's going to be an attraction between the two. Now, the other thing he learned is that you have 2 like charges. They're going to repel each other. And so those 2 protons don't want to be next to each other. They're going to be really unstable, and the neutrons and the strong nuclear force actually hold them together. Now, did you see what happened to the arrows? The arrows got larger when we looked at the protons. And that's because, according to Coulomb's law, as those charges get closer and closer and closer, then the forces get larger and larger and larger. And so it's sometimes referred to as the inverse square rule. And so let's get to Coulomb's law. And why is it important? Well, again, it shows us that positive and negative attract. And it also tells us that if we have 2 like charges, they're going to repel. But the closer they get, the bigger that charge is going to be. And so Coulomb's law tells us the force between charged particles is proportional to their charges. So all you do is just multiply the 2 charges, and that's going to give you the magnitude. It also tells us that it's inversely proportional to the square of their radius. In other words, how far they are apart. So if things are far apart, it's going to be less charge. As they get closer and closer and closer, that charge is going to get greater. It's very similar to the gravitational, Newton's law of universal gravitation. This just deals on the small level with charges. Now, in chemistry, it's important because we can use Coulomb's law to predict ionization energy. Ionization energy is the amount of energy it's required to create an ion. And so what's an ion? It's when you're either losing or gaining an electron. And so ionization is the energy required to remove an electron. And in chemistry, in science, we can actually measure ionization energy using something called photoelectron spectroscopy, or PES. Now that seems confusing, but it's actually a really simple concept and has huge implications when it comes to understanding what an atom actually looks like. So we can use the data to predict the shell structure. So how do we know that we have these shells and orbitals? A lot of that is predicted through Coulomb's law, but it's also verified through PES. So who was Coulomb? He was a French physicist, and what he was doing was studying charges. A lot of people thought there was some law that was could be applied to charges, and he was the first one to really quantify that. So essentially, if we have 2 like charges, they repel. And if we have 2 unlike charges, there's going to be an attraction. And here's the equation right here. You have a Coulomb's coefficient, and then we're going to have multiplying the charges, and then we're going to take the radius squared. Now, how did he discover this before we had electronics and even electricity had really been discovered? He used something called a torsion balance. And this is one of his sketches of a torsion balance. It looks a little complex, but it's really simple. All he would do is he would take a sphere and he would charge that sphere. And so we're talking about static electrical energy. And so that was suspended by a fiber that went all the way down here in the torsion balance. So he'd give this a positive charge, and he would give this a positive charge as well. And so if we have 2 like charges, what's going to happen when I bring this one? We can see it right here. As I bring this closer, what's it going to do? You can see that it's going to push it away. It's going to repel. And so it would twist this fiber, and he could measure it. You can kind of see the scale on the side. He could measure how far it went. He would then move it away, and he would touch this sphere to another sphere that didn't have a charge. And what it would do is it would transfer half of its charge to that uncharged sphere. He would then bring it back again, and it wouldn't move as far. And so he was able to quantify Coulomb's law using a not super sophisticated torsion balance. And so why is this important in chemistry? We can use it to measure ionization energy. And so what's ionization energy again? It's the amount of energy required to remove an electron. And so think of it as just a little hand that has to come in and grab this electron and pull it off. So that's the ionization energy. And so it's going to depend on Coulomb's law how big that ionization energy is going to be, because that proton wants to hold it in place. And so let's say we were to look at something that's a little larger. So this is lithium. And so lithium is going to have this outer electron out here. And since the distance is greater, in other words, that radius is larger, you're going to require a smaller amount of ionization energy to pull it off. And so that Nobel Prize was awarded to Albert Einstein for his discovery of the photoelectric effect. And what that means is if you hit metal with photons or hit metal with light, what it'll do is it'll eject these electrons, and we call those photoelectrons. And so hold on to that idea. It's going to become really important in just a second. But let's build an atom for a second. And this is a simulation from PHET. What you can do, you could go to the website right down here. What you can do is you can just start dragging things in, and then it'll actually build that atom for you. So let's do that. So let's say I drag a proton in. I've now created hydrogen. You can see on the periodic table that's going to be H. It's got one atomic number. But let me just throw an electron in there, and where does it go? It goes right there. What's holding it in place is going to be Coulomb's law. They're opposite in charge, and so they're going to be held together. Well, what happens if I throw another proton in? Now we've got helium, but look how unstable it is. Why is it so unstable? It's because those are like charges, and so they want to repel each other. Luckily, and it would never exist like that. Luckily, if we add some neutrons to it, then we can stabilize it, and so that's not going to decay. Now let's add another electron. It's going to sit in this shell. And so we've got 2 electrons in this first shell. Let's make it from helium. Let's move up, make it a little bit of unstable lithium. We'll stabilize that with a neutron. Now let's add another electron. What happens? Well, it sits right there. In other words, it's in the outer shell. And this is in the outer shell, and this is in the outer shell. So why is it that those first 2 electrons are going to be on the inside shell, and the outer electrons are going to carry, or excuse me, those additional electrons that we add are all going to be thrown to the outside? That has to do with quantum mechanics and quantum physics. And so it's quantum numbers that are determining that. But how did physicists figure this out? How did chemists figure out that there's going to be a 2 in the first, and then we're going to have 8 in the next, and we're going to have all these orbitals? Well, we owe it to the photoelectric effect. And so going back to that again, that's Einstein's theory that if you hit matter with light, it's going to eject these photoelectrons. And so let me show you photoelectron spectroscopy. And so what is that? You basically have a photon source on one side. And so you're going to have a source of light on one side. And so that could be infrared light, it could be UV light, it could be X-rays. The energy of those photons is determined according to the equation where energy is equal to hv, where h is Planck's constant and v is going to be the frequency of the light. So basically in this machine, you can vary the energy of those photons that are coming out. They'll strike the matter that you want to study that's sitting inside a vacuum, and that's going to eject electrons, so photoelectrons, and those photoelectrons will be captured up above so we can measure them. And so this is a pretty simple setup. What are you doing? You're hitting matter with light, and then you're measuring the electrons that come out of it. And so let's look at hydrogen. If we're looking at a sample of hydrogen, we're going to create a spectrum, or a photoelectron spectrum. And so we're going to have energy across the bottom. That's the amount of energy that we're introducing with the light. And then we're going to have the number of electrons on the side. And so what happens when you turn on the machine is you can just vary the energy, and eventually you'll hit a point where you get a bunch of electrons coming out. So why is that? Well, what we're doing is we're changing the amount of energy to the point where we hit ionization energy, and then boom, we're going to release all of those electrons from hydrogen. And so we're going to get a peak at, we'll just call this 1.3 and think of it as an amount of energy. Now let's go to helium. What do you think that's going to look like? Well, helium has 2 protons on the inside, so it's going to have a different amount of ionization energy. And so if we hit that with light, watch what happens. Okay, it's different amount of energy. You can see that we need more energy to eject those electrons, but look how big the peak is. Now let's compare that back to hydrogen. Hydrogen had a peak like this. Helium had a peak like that. Why is this twice as high as this one? It's because it has twice as many electrons. It's because we're ejecting 2 electrons when we tune that frequency to the right ionization energy. Okay, you think you got that? Let's go to the next one. What do you think will happen with lithium then? If we hit lithium with energy, well, we'd already talked about this outer one is going to have a low amount of ionization energy. So let me show you the spectrum for lithium. Wow, what do we get here? Well, we get one peak that's going to be 1 electron that's going to have low ionization energy, and that's going to be this one right here. But then we're going to have a double peak, in other words, 2 electrons, that's going to be way more energy. Why is that? Lithium's going to have way more protons. And so what's cool about photoelectron spectroscopy is we can actually verify the predictions that we made with Coulomb's law. So could you fill in this concept map? Coulomb's law is the force between charged particles. And how is that related to their magnitude and radius squared? Could you fill in those 2 blanks? And what is that technology, do you remember, that measures ionization energy? And then what is ionization energy? It's the energy required to do what? Let's see. So it's the force between charged particles is proportional to the magnitude, in other words, just multiply the charges, inversely proportional to the radius squared. That technology is called photoelectron spectroscopy, and then ionization energy, remember, is the amount of energy required to remove an electron. So what did you learn? You should have learned that we can explain the distribution of electrons in an atom or ion based on data. And so we can predict data using Coulomb's law, and we can also verify it using PES. We can analyze the data, and we can look for patterns and relationships. And we're going to get more into those patterns and relationships in the next video, but I hope that was helpful.